Hi, this video will explore a basic controller area network, in short CAN. The RS6M4 comes with two CAN channels. Controller area network is a widely used communication protocol known for its reliability and efficiency in high-speed communication between microcontrollers, sensors, and actuators in the automotive and industrial automation. It operates on a decentralized architecture, allowing nodes within the network to independently transmit and receive messages without the need for a central controller. This decentralized approach enhances flexibility and scalability, making it easy to integrate additional nodes into the network. The CAN architecture involves a microcontroller equipped with a CAN controller and a CAN transceiver connected to the CAN bus. Data is first exchanged between the CAN controller and the CAN transceiver, which is then relayed to the CAN bus. A common bus allows the nodes to communicate with each other independent of all other nodes. Due to its shared bus, nodes can be added or removed from the system without interrupting the other connected devices. The hardware connections for our project includes a generic CAN transceiver module, which is connected to the EK-RS6M4 board through the CTX and CRX pins. A 120 ohm resistor between the CAN-L and CAN-H is to be used as a termination resistor as per CAN protocol. To implement a simple example, we shall develop a loopback communication between the receiver and transmitter of a single CAN channel. In this example, the transmitter will transmit the data and the data will traverse the CAN bus to arrive at the receiver's end. This implementation is called external loopback mode, which is a test mode for CAN peripheral. During this process, data is transmitted to the CAN transceiver and is received back into the CAN unit of the microcontroller. We will now proceed to build the project. We start by opening a new C++ project in E-Square Studio. We shall select the EK-RS6M4 board as usual. For the rest of the configurations, we can maintain their defaults. Once the project has loaded, we can start configuring the peripheral ports. For this task, we're only concerned with the CAN transmission. So, we need to seek out the CAN stack from the connectivity menu. We will use channel 0, so nothing much to change there. You will notice the CRX and CTX pins are not assigned any pin number. So, we got to check from the pins tab what's going on. First, we can see that the pins that could have been assigned to the CAN controller are not available. So, those must be configured to some other functions. If we navigate to the individual pins, we can see that the pin 202 is currently configured as an SPI channel. Since we are not going to use the SPI protocol, we can straight away disable it. This would free up some pins for the CAN. Going back to the CAN configuration, we can now see that the pin 202 and pin 203 are available to be assigned for CAN communications. Once we have assigned them, we can see that these appear in the configuration properties as well. Next, we need to make sure a callback function has been named. Then, we need to make two important changes. At the mailbox settings, we need to assign mailbox 4 to receive type and mailbox 31 to transmit type. Once that is checked, we can generate the project contents. This exercise will enable the project to include all the necessary header files with the configurations just made. We will start coding from the hullentry.c file. We can enable a better view by selecting the C++ perspective. We shall first declare the two CAN frame variables to hold the transmission and reception data. The CAN frame data type is a custom structured data type defined in the r_can_API file. It contains information on the CAN ID, CAN data type, including the data itself. The header file is included through the hull_data header file and is automatically included when we added the stack. For the next part, we are going to add some flag variables to hold the data transfer status during different stages of the program. Specifically, we are going to have two flags for the reception and transmission, one flag for error, and another variable to hold the reception ID. We are going to have two more variables to be used in our program. We will also have to define some constants regarding the CAN data exchange. We set the delay duration to be used by the CAN channel. We also set the identification value for the CAN mailboxes. Mailbox 4 serves as the receiving mailbox where the frame is sent to, while mailbox 31 functions as the transmitting mailbox from which the frame is sent out. Finally, we define the frame data transmit length. Now, we shall define the callback function. The callback function will mainly execute a switch statement based on the event status. The first status we're interested in is the reception complete status, which is triggered when a data has been received by the CAN channel. We will also assign the data received to the different variables we had previously created in our program. The arguments for the callback function are already defined by the FSP under simple pointers, and we can get the callback function in the Developers Assistance menu. In this scenario, the arguments would have the information on the frames. In a similar manner, we are also going to have a transfer event. In this event, we are simply going to set the transfer flag true. Then we are going to add the break statement as the default for this switch case. Then we close our switch statement and the callback function. We can now start by writing the hull entry function. As usual, first we will declare the FSP error variable that holds the return value of the FSP API calls. Then we're going to add some variables associated with the CAN transfer protocol. While the timeout is a numeric variable, the CAN operation mode and CAN test mode are custom enumerated data types that holds unique values representing a particular protocol. Once the variables are declared, we will make API call to two FSP functions. The first will open the CAN channel. The arguments are already satisfied. We use the assert macro to make sure the function has executed successfully and returned the desired status. Next, we call the mode transition function. This is where we need to pass the values for operation mode and test mode. We have previously defined their values in operation_mode and test_mode variables, so we can pass the variable names. We are also going to set the received frame values to zeros. We will then create a while loop. We will also declare a variable to hold the comparison result for transmitted and received data. The transmit frame data needs to be written before the transmission can begin. We will enter values for three fields: the frame ID, the frame type, and the data length code. It seems like the frame ID value is not recognized. Let's see our definitions. Okay, the _4 is missing. We add that and it should resolve our warning. We will use a for loop to populate the transfer data buffer. For each byte, we're going to add some values based on the index of the data byte. So we add a 2 and another number that will be incremented in each iteration of the while loop. Now, for the write operation, we will add a delay first and set the flags to false. Then we shall call the CAN write API. As its arguments, we will have to write the transmission mailbox number and the transmission frame, This is followed by the assert macro. As the write operation is executed, we can add some error handling, for example, a timeout. We shall add a general timeout delay and then check for the error flags. If the write operation is not successful and the error flag status is set to true, the program will halt. In order to update the error flag, we can make use of the callback function and add a new case for lost messages. If there are no errors, we can check the transmitted and received bytes using the memory compare function. As arguments, we shall put the transmit and receive data. If the return is not 0, that is, the data does not match, then we set the state variable to 0, indicating a non-match. Otherwise, we will set the state variable to 1, signaling a data match. Now, looking back in the code, it's a good idea to include the CAN bus error events in the callback function and also set an error flag. Once the program has finished, we can build it and upload to our board using the debug function. We can utilize the expressions tab to monitor the transmit and received frames. We notice that the state remains at 1 while the transmit and received data changes, which means successful data transfer over the CAN channel. And that brings us to the end of our today's presentation. See you in the next video.